Hello, my name is Saha Zahiri from Oxford Brookes University. Welcome to this presentation. In the next 15 minutes, I'm going to talk about natural experiment that was carried out to measure changes in indoor environment and electricity use in dwellings in Oxford in the UK after installation of smart heat pumps. In this presentation, I'm going to give some backgrounds and context regarding the UK government target to accelerate the path to net zero and installation of heat pumps. I will also provide insight into study objectives and methods and characteristic of case study dwellings, followed by results and findings and final discussion. Moving to background and context, to accelerate the path to net zero, the UK government announced its 10-point plan for green industrial revolution in 2020, which includes a challenging target to install 600,000 heat pumps per year by the end of 2028. In addition, 90 million heat pumps need to be installed across the country by 2050, which will be a step change the 20,000 heat pumps unit that are currently being deployed across the country every year. To achieve this target successfully, it's important to balance electricity demand and supply locally, which will also avoid the expected surge in heat pumps installation to exceed the capacity of the current UK electricity system. In addition, deploying smart heating controls coupled with heat pumps can also help with local grid balancing while maintaining comfort of the resident. With these contexts, and also as I mentioned earlier, this study used a natural experiment approach to get insight into changes in indoor environment and electricity use, pre and post heat pump installation across 9 social housing dwellings in Oxford from October 2020 to December 2020. The study used a mixed method approach, included household survey to identify social demographics and ways residents heat their homes, physical characteristics using energy performance certificate data before heat pump installation, and monitoring of indoor temperature and relative humidity in 9 dwellings with 15 minutes interval using Bluetooth-enabled hobo data loggers that were located in living rooms of each dwelling. Electricity use was also monitored in 2 dwellings with 15 minutes interval using loop device, which was connected to electricity meter of each dwelling. The 9 dwellings included 5 bungalows and 4 flats located in socially deprived area in Oxford. From EPC certificates, higher energy rating in flats were identified compared to bungalows with EPC of D and C. This was possibly due to the lower exposed area in flats compared to the bungalows. EPC data also showed higher predicted heating demand in bungalows compared to flats before heat pumps. And in order to improve energy efficiency of bungalows, field cavity walls were installed following the installation of heat pumps in autumn 2020. Studying the household characteristics showed no association between annual income and annual energy cost, although all dwellings had single occupancy and the average annual income of the resident was less than £15,000. Similarly, there was no correlation between predicted heating demand that obtained from EPC and annual energy costs self-reported by residents, although all dwellings have similar size and occupancy. This confirmed the impact of residents' behavior on energy use as compared to dwellings characteristic and household characteristic. This can also be an implication for local authorities and energy companies who use EPC to target dwellings for energy retrofits for the future across the country. Studying environmental monitoring data across 9 dwellings shows interesting result. Significant increase observed in indoor temperature in bungalows after heat pump installation. This was due to the improved air tightness along with constant heating as compared to flats. The mean indoor temperature in bungalows also increased to 23.4 degrees Celsius after heat pump from 20.4 degrees Celsius pre-heat pump installation. The highest mean temperature of 25 degrees Celsius and above observed in mid-terrace bungalows after heat pump installation, since the mid-terrace bungalows had smaller exposed area compared to end-terrace bungalows. And interestingly, in contrast to bungalows, flats had no major changes in indoor temperature. And in fact, the indoor temperature after heat pump installation reduced to 22.5 degrees Celsius from 22.6 degrees Celsius. Studying the distribution of indoor temperature across 9 dwellings showed that indoor temperature were more stable across the dwellings after heat pump installation. However, wide range of temperature identified in bungalows. This show a variation in heating preferences amongst the residents. Also, it shows that smart control used in an unintended ways to overcome low output temperature of the heat pumps. This also reinforced to train the resident to use low temperature output heating to get benefits of, to maximize comfort and to minimize energy cost. In contrast to indoor air temperature, indoor relative humidity ranges were almost similar across 9 dwellings before heat pump and ranging extremely low to extremely high. However, after installation of heat pumps, due to the continuous heating as indicated by higher indoor temperature, indoor relative humidity reduced significantly in bungalows compared to the flats. The changes in indoor relative humidity in flats was subtle in line with minor changes in indoor air temperature after heat pump installation. Moving to next slide regarding electricity use analysis. An increase in daily electricity use identified across the dwellings after installation of heat pump. This was due to the colder weather and constant heating. In addition, daily electricity use in flats after heat pump was lower compared to bungalows. This was also due to the residents' preferences to keep the windows open when the heating was on, which was observed during the site visits. To assess the efficiency of the heat pumps and account the weather, electricity use was also normalized for outdoor temperature, showing 49% reduction after heat pump installation. This confirms the efficient running of the heat pumps despite the user preferences. In addition, mean daily indoor temperature and electricity use profiles showed rise in electricity use during the peak periods from 4 p.m. to 7 p.m. This reinforced the need to integrate time of use tariff to encourage load shifting amongst the residents. It's also worth noting that despite more distributed electricity use during daytime after heat pump installation, it's important to utilize renewable electricity locally for grid balancing and to reduce network pressure. And finally, To sum up the findings which were discussed in this presentation, we can conclude that indoor temperature were more stable after installation of heat pumps across the dwellings. However, wide variation of indoor temperature ranges identified across the dwellings, despite having similar size, number of the occupants, and occupancy patterns. As compared to the flats, bungalows experience excessively high indoor temperature of 25 degrees Celsius up above, and consequently low indoor relative humidity due to the improved air tightness as a result of cavity wall insulation, continuous heating, and limited windows opening. Since no correlation identified between annual energy cost observed by the resident, mentioned by the resident and EPC rating, it's important to obtain details about occupancy characteristic when data for EPC rating are collected. An increase on electricity used for heating during the evening peak, especially after heat pump installation, make a strong case for connecting these dwellings to time of use tariff with different prices during the peak and off-peak periods, which is in line with wholesale prices. However, since this can introduce automation and complexity for residents, it's important to strengthen the engagement with residents and improve their knowledge and understanding on low carbon heating and time of use tariff to get the best benefits of heat pump installation and smart heating control. And thank you very much for listening.